So for today, we will look at example 10.3, design of non-slender column bent above major axis. Yeah, so major axis here is Z axis. Right, classification for the column is brace non-slender column. So it is brace short column. Yeah. FCK 25, FYK 500, exposure class XC1, fire resistance is 1 hour. Design life is 50 years. Column size is 250 times 300. So it's given the cross section B is on the vertical dimension and H is on the horizontal dimension. Yeah, and you can see ZZ axis will cross H and YY will cross B. Yeah, and moment Z X at Z axis. Yeah, this is the bending moment diagram for Z axis. Okay, we have NED 1200 kilonewton and MZ top is 35 kilonewton meter while MZ bottom is negative 25 kilonewton meter. Yeah. Effective length is given as 4.2 meter. Diameter link is assumed to be 6 and diameter bar is 20 mm. So the first step is to determine nominal cover, yeah, because when you are given exposure class, fire resistant and design life means that you need to calculate for C norm. Okay, so to calculate for C norm, you can refer the formula on design appendix. Yeah, we have C norm equation 4.1 equals to C min plus delta C def. And C min minimum cover with regard to bond, we can refer to table 4.2 for separated arrangement of bars. The minimum cover would be diameter of bar. Okay, so table 4.2, diameter of bar is 20, so C min B is 20 mm. And then for minimum cover with regards to durability, we need to refer to table 4.4 on design appendix. Okay, so design appendix. For structural class 50 years, it's S4. Okay, exposure class is given as XC1, therefore C min dur is 15 mm. Okay, and then for fire resistance, we have R60 fire resistance. For column, we need to refer to table 5.2a. Yeah? So this table 5.2a is not provided in the design appendix, but you can find it on the Eurocode, yeah? EN 1992-1-2. Okay, so this is table 5.2, minimum column dimensions and axis distances for columns with rectangular or circular section. Yeah. So over here, for standard fire resistant R60, okay, we need to assume mu Fi, mu for the fire. So mu is it's given as NED divided by NRD. Yeah, NED is the axial load in fire condition divided by the design resistance of column at normal temperature conditions. Yeah. So we don't know what is the design resistance of column at normal temperature conditions because we want to design for the column. So therefore, you can assume the value of mu. Yeah. You can assume mu 0.2, 0.5 or 0.7. Okay. For example 10.3, if I look at the answer ASD 36, this is for mu fire equals to 0.5. Yeah. So mu fire 0.5. Okay, so 36, this is column width, okay, slash axis distance A. So column width 200. So ASD is 36. Yeah. So this is B minimum. Okay, let's check our B. Our B is 250. Okay, so you can either use 200 so that ASD is 36, or if you want to interpolate, you can do so. So if it's 250 here, meaning that ASD would be 5 divided by 2, 2.5, so 33.5 if you want accurate answer, yeah, accurate value. Okay, so I'm gonna stick with 36. Okay, so ASD is 36, therefore we can calculate C min with regard to fire is ASD minus diameter length minus diameter bar divided by 2, so 36 minus 6 minus 20 over 2, we get 20. Right? So compare which is the maximum value. So therefore it can be C min B or C min fire. So it will be 20. So C min is 20 and delta C depth is 10. So therefore C norm is 30 mm. Okay, so that is the nominal cover. All right, next is to calculate design moment. Yeah. So if you refer to my updated notes, okay, so the design moment for short column is given by MED equals to maximum of M naught 2 or NED times E naught. Yeah. So M naught 2 is you have to find the maximum of absolute M top or M bottom and then plus the M imperfection. Yeah. So we have moment at top is, okay, let's look here. Right. So M naught 2 is this. Yeah. M plus NED times EI, the moment of imperfection. Yeah. So M top and bottom is 35 because we have bottom 25. So maximum is 35. M02 equals to maximum of M top or M bottom, yeah, absolute value plus M imperfection, yeah. So maximum of M top is 35, M bottom is 25 plus NED times NED is 1200. Okay, maybe we can calculate that separately. Yeah, MI. So this would be maximum is 35 plus NED. Okay, NED is 1200 multiplied by EI. Yeah, so EI, if you refer to notes, EI would be L naught over 400. Okay, so L naught over 400 is this. So 10.5 mm. And then you convert to meter, it would be 0.0105. Right, so m naught 2 would be 47.6 kilonewton meter. So that is m naught 2. And then minimum moment due to minimum eccentricity, NED times E naught. E naught is H over 30 or B over 30. So H over 30 when bend about major axis, yeah? And you use this one when it's the bending is about minor axis. Okay, so it will be H over 30, but must be larger than 20. So H is 300. Yeah, you can see H is 300. Divide by 30. So we get 10. And it is not larger than 20. So therefore use E naught equals to 20 mm. So therefore M min is 24 kilonewton. And then you will get MED is the maximum of 47.6 as well as 24. So therefore MED is 47.6 kilonewton meter. Yeah, so that is the design moment. All right, and then next step is to calculate D2 distance. Yeah, so if you refer to lecture notes, this D2 distance is here. Yeah, so that is the distance from top of the column until half of reinforcement at top. Yeah, so that is C norm plus diameter length plus diameter bar divided by 2. Okay, so C norm plus diameter length plus diameter bar divided by 2, we get D2 is 46 mm. So D2 over H is 0.15. Yeah, so use chart D2 over H equals to 0.15. Okay, and then calculate N over BHFCK. Calculate M over BHFCK. Okay, and then we can look at design chart. Okay, design chart D2 over H 0.15. Okay, this one. Okay, and then we have N over BHFCK 0.64 and 0.08. So 0.64 is about 0.05678. 0.08 is here, and then 0.64 is about here. Okay, so 64 more or less, and then 0.08. So that is the intersection. So that is about 0.34. Okay, 0.34. So AS FYK over BH FCK is equals to 0.34. Okay, let's see. Okay, it says here 0.35. All right, good enough. Okay, so rearrange the formula. We get AS required 1313 mm square. Yeah, so you can refer to design appendix, last page of design appendix. Okay, we will use table number 1 because this is for beam and column. Okay, so for bar size 20, AS required is 1313. So 1313 you can provide for H20. Okay, so provide for H20. And then calculate AS min and calculate AS max. Yeah. Right. So that AS min is 150, 276. And AS max is 3000. Okay, so the AS provided is okay. Okay, and then based on AS min, yeah, because bending occurs about major axis, yeah. If bending occurs about major axis means that the bending will um, occur on the left side or the right side of the z-axis, yeah, because this is our column. Okay, so this is z-axis, so it will bend to the left or to the right of z, yeah. So therefore we have to strengthen it with additional reinforcement bar. Okay, you can provide 6H20. So 6H20 means that if you use 6H20, the area would be 1890. Yeah, 1890, or you could provide a smaller diameter. Yeah, smaller diameter or smaller bar size. In this case, you can refer to AS min. Yeah, so AS min, if we choose 276, so 276, and for bar size 12, so bar size 12, so provide 2, so therefore total would be 1260, and that one is 226. So 2H12. So total would be 1260 plus 226. It's 1486. Okay, so for 2H12, total would be 1486. 1486 mm square. Yeah. All right. So for column, because you cannot minimum bar size, yeah, as stated in the lecture notes, it should be minimum 12 mm. Yeah, you cannot use lower than 12 mm. Alright, so that is the reinforcement for main reinforcement, yeah, for the column. Next is to design for the link. Okay, so for link design, this is equation for AS min just now, yeah? Okay, whichever is the greater. And that is for AS max. This is for AS max. And for the design of link, you have to design for minimum link diameter as well as the spacing. Okay, so for minimum link diameter, it would be minimum of 6 mm or 1/4 of diameter, maximum diameter of longitudinal bar. It should not be less than 6 mm, yeah? So minimum 6 mm or 1/4 of diameter, maximum diameter of bars. So the larger of is not minimum, yeah, it's maximum. So it should be maximum okay, maximum 6 mm or that. So if we use this formula, maximum of 6 mm or 1/4 of diameter maximum, so it will be maximum of 6 or 1/4 of 20. So that is 5. So therefore, we will choose 6. Yeah. 6 mm. All right. And then for spacing, S max, SL max, yes. Link spacing maximum is given by minimum, the least of the following, minimum of 20 times diameter minimum bar, lesser dimension of column, and the other one is 400 mm. Okay, so if we want to write that, so SL max equals to minimum of 20 times diameter minimum for bars, lesser dimension of column, or 400 mm. So that would be minimum of 20 times 20. Lesser dimension is 250 or 400. So therefore 20 times 20 is 400. So minimum would be 250 mm. Okay. All right. So we can provide H6 240. Okay, and then at section 300 mm below and above beam, and at lap joint Yeah, the spacing should be lesser, whereby we take it as 0.6 times the spacing that we provide, yeah, for the column, yeah. So it will be 144 mm, so use H640. So at the lap joint here, the spacing would be H6 140 for the link. Okay, at 300 mm below and above beam. So also at where you have lap. Okay, H6 140. Okay, for the rest here, we can use H6 240. Right, and the main reinforcement is this one, main reinforcement. Here we have for H20 and to H12. Okay, so that's it for the design of a short column with azimuth and uniaxial moment.